Welcome to today's paper reading. Today's paper is titled, Phi-3 Technical Report, a highly capable language model locally on your phone. This technical report introduces Phi-3 Mini, a 3.8 billion parameter language model developed by Microsoft, which can be deployed on a phone. The abstract introduces Phi-3 Mini, a language model with 3.8 billion parameters trained on 3.3 trillion tokens. This model performs competitively with larger models like Mixtral 8x7b and GPT 3.5, achieving 69% on the MMLU benchmark and 8.38 on MTBench. Notably, Phi-3 Mini is compact enough for deployment on mobile devices. The training dataset for Phi-3 Mini is an expanded version of that used for Phi-2, consisting of heavily filtered public web data and synthetic data. The model is also aligned for robustness, safety, and chat format. Additionally, the abstract mentions larger models, Phi-3 Small and Phi-3 Medium, which are 7 billion and 14 billion parameter models trained on 4.8 trillion tokens, showing improved capabilities over Phi-3 Mini. The rapid advancement in AI over recent years is largely due to the global effort to scale up models and datasets. Large language models, LLMs, have grown from a billion parameters to trillion parameters today. This growth follows scaling laws, which assume a fixed data source. However, the emergence of frontier LLMs has disrupted this assumption, allowing new ways to interact with data. In previous works, it was shown that combining LLM-based filtering and synthetic data can enhance smaller models' performance. For instance, Phi-2, with 2.7b parameters, matched the performance of models 25 times larger. In this report, we introduce Phi-3 Mini, a 3.8b parameter model trained on 3.3 T tokens, which can be inferred locally on a modern phone. Despite its small size, Phi-3 Mini achieves quality on par with models like Mixtral 8x7b and GPT 3.5, demonstrating the power of data-driven optimization. The Phi-3 Mini model is based on a transformer decoder architecture with a default context length of 4K and a vocabulary size of 320,641. The Phi-3 Small model, with 7B parameters, has a default context length of 8,192 and a vocabulary size of 1003522. It uses a tick token tokenizer for better multilingual tokenization. The Phi-3.5 Mo model adopts a mixture of experts architecture, incorporating 16 expert networks and a vocabulary size of 32,064. This model selectively activates parts of modules on specific inputs to improve efficiency. Figure 1 illustrates the block sparse attention mechanism in the Phi-3 Small model, featuring 2 local blocks and a vertical stride of 3. The table details the keys and values attended to by a query token in block 8, with blue indicating local blocks, orange representing remote/vertical blocks, and gray showing blocks that are skipped. Figure 2 illustrates the performance of the 4-bit quantized Phi-3 Mini model running natively on an iPhone equipped with the A16 Bionic chip. The model is capable of generating over 12 tokens per second, showcasing its efficiency and suitability for on-device, real-time language processing tasks. Figure 3 illustrates the scaling law close to the data optimal regime for various Phi models, Phi 1.5, Phi 2, Phi 3 Mini, Phi 3 Small, compared to the Llama 2 family of models, 7B, 13B, 34B, 70B. The graph plots the logarithm of the MMLU error against the logarithm of the model size, showing how the error decreases as the model size increases for both series of models. This comparison highlights the performance of the Phi models in relation to the Llama 2 models, all trained on the same fixed data, indicating the effectiveness of the data optimal regime in reducing error rates as models scale. In this section, we present the results of the Phi-3 model on various standard open-source benchmarks that measure reasoning abilities. We compare Phi-3 to several other models including Phi-2, Mistral 7BV0.1, and Mixtral 8x7b. The benchmarks include MMLU, HelloSwag, and ANLI, among others. All evaluations were conducted using few-shot prompts at a temperature of 0, ensuring consistency across models. The evaluation tool used is a Microsoft internal system, which was not optimized specifically for Phi-3, maintaining a fair comparison. The authors developed two enhanced versions of the Phi-3 models, Phi 3.5 Mini and Phi 3.5 Mo, to incorporate multilingual and long context capabilities. These models were trained with additional multilingual and long text data using the long rope method and a mixed context window approach. This expansion allowed the context length limit to increase from 4K to 128K tokens without degrading performance on 4K context tasks. Performance comparisons on multilingual tasks show that Phi 3.5 Mini significantly outperforms Phi 3 Mini in several languages, with average scores of 55.4 and 47.3, respectively. The Phi 3.5 Mo, due to its larger model capacity, achieves an even higher average score of 69.9. Both models also demonstrated superior performance on the RepoQA and Ruler benchmarks compared to other open-source models, although a performance drop was observed on the Ruler task with the 128K context window, suggesting a need for more high-quality long-context data in future model versions. Table 1 presents the comparison results of various models on the RepoQA benchmark. The table includes the context size, CTX size, for each model and their performance scores in languages such as Python, C++, Rust, Java, and TypeScript. The average scores across these languages are also provided, offering a comprehensive view of each model's capabilities in handling multilingual tasks. Figure 4 illustrates the performance comparison of Phi 3 Mini, Phi 3.5 Mini, and Phi 3.5 Mo models on multilingual tasks. Notably, Phi 3.5 Mini shows significant improvement over Phi 3 Mini in languages such as Arabic, Chinese, Russian, Ukrainian, and Vietnamese, achieving an average multilingual score of 55.4 compared to 47.3. The Phi 3.5 Mo, due to its larger model capacity, achieves an even higher average score of 69.9, outperforming both Phi 3.5 Mini and other open-source models on the RepoQA task. This demonstrates the enhanced multilingual capabilities of the Phi 3.5 series models. Table 2 presents the comparison results of various models on the Ruler benchmark. It highlights that Phi 3.5 Mo significantly outperforms other open-source models and offers performance comparable to Gemini 1.5 Flash. Additionally, Phi 3.5 Mini achieves performance levels comparable to much larger models like Mistral Nemo 12B and Llama 3.1-8B. The table also indicates that Phi 3.5 Mo achieves above 90% of the average performance of GPT-4o Mini across various language benchmarks. The development of Phi 3 Mini adhered to Microsoft's responsible AI principles, focusing on safety alignment post-training. This involved a comprehensive red teaming process and extensive automated testing across multiple harm categories. Datasets emphasizing helpfulness and harmlessness, along with in-house generated datasets, were utilized to address these categories. The result was a significant reduction in harmful response rates, as evidenced by the comparison shown in Figure 5. Additionally, the model's performance was benchmarked against other models, with metrics including ungroundedness and harm severity, providing a comprehensive view of its safety profile. Figure 5 illustrates the comparison of harmful response percentages by the Microsoft AI Red Team for Phi 3 Mini before and after the safety alignment process. It is important to note that the harmful response percentages shown in this chart are inflated due to the Red Team's adversarial approach, which involved inducing Phi 3 Mini to generate harmful responses through multi-turn conversations. This comparison highlights the effectiveness of the safety alignment in reducing harmful responses. Table 3 presents a detailed evaluation of the Phi 3.5 Mini and Phi 3.5 Mo models compared with recent state-of-the-art pre-trained language models. The results show that Phi 3.5 Mini achieves performance comparable to much larger models like Mistral Nemo 12B and Llama 3.1-8B, while Phi 3.5 Mo significantly outperforms other open-source models, offers performance comparable to Gemini 1.5 Flash, and achieves above 90% of the average performance of GPT-4o Mini across various language benchmarks. The Phi 3 Mini model, despite its advanced language understanding and reasoning abilities, faces significant limitations due to its size. It struggles with tasks requiring extensive factual knowledge, as evidenced by its low performance on the Trivia QA benchmark. However, these limitations can potentially be mitigated by integrating the model with a search engine to enhance its knowledge base. Additionally, expanding the model's language capabilities to include more multilingual data shows promise, particularly with the Phi-3 small model. Despite efforts to mitigate issues through carefully curated training data and targeted post-training improvements, challenges such as factual inaccuracies, bias amplification, and safety concerns remain. These issues require ongoing attention and tailored evaluations for specific use cases to ensure safe and effective model deployment. Table 4 presents a comparison of Microsoft's internal RAI benchmark results for Phi-3 models against other models and multi-turn conversation scenarios. The metrics evaluated include ungroundedness, third-party harm, DR1, harmful content continuation, DR3, and harmful content summarization, DR3. Lower values indicate better performance across all metrics. Key figures include an ungroundedness score of 0.603 for Phi-3 Mini, a third-party harm, DR1, rate of 0.240, and a harmful content continuation, DR3, rate of 0.007. The Phi-3.5 vision model is a 4.2 billion parameter multimodal model designed to process both images and text. It consists of a CLIP VTL/14 image encoder and a Phi-3.5 mini transformer decoder. During pre-training, the model processes 0.5 trillion tokens, with a maximum image resolution of 1344 by 1344. The model is then fine-tuned using supervised methods and direct preference optimization, with a focus on multimodal tasks and safety, utilizing datasets totaling 33 billion tokens. Figure 6 illustrates the performance of Phi-3 Mini in generating responses with and without web search capabilities. On the left, the model's completion without search results in an incorrect response. On the right, the model's completion with search not only corrects the inaccuracy but also provides more specific details. This example highlights the importance of search integration for enhancing the accuracy and specificity of model outputs, particularly in contexts like predicting the location of future Olympic Games. Figure 7 demonstrates Phi-3.5 Vision's proficiency in natural image understanding and reasoning. This capability spans various domains and tasks, including general image understanding, chart/table/diagram reasoning, PowerPoint comprehension, multi-image comparison, video summarization, and model safety. The multimodal supervised fine-tuning (SFT) data comprises approximately 33 billion tokens. For direct preference optimization (DPO), both text and smaller-scale multimodal datasets are utilized. This dual training approach ensures the model maintains robust language capabilities while excelling in multimodal reasoning. Table 5 presents the comparison results of Phi-3.5 Vision on various public MLM benchmarks. The evaluation was conducted using the same pipeline for all models to ensure comparability, except for MM1-3B Chat and MM1-7B Chat, which are not publicly available. The evaluation setting followed Lava 1.5, without any specific prompts or image preprocessing. The reported numbers might differ from other published results due to slight variations in prompts. Table 6 presents the evaluation results of Phi-3.5 Vision on public multi-image and video benchmarks, specifically Blink and Video MME. The table highlights Phi-3.5 Vision's competitive performance, often surpassing baseline models. Notably, for the Video MME benchmark, frames are uniformly sampled to ensure a fair comparison across models. This approach guarantees that all models receive the same input information, thereby maintaining the integrity of the evaluation process. The results underscore Phi-3.5 Vision's robust capabilities in multi-image understanding scenarios. Table 7 presents a comparison of Phi-3.5 Vision's performance on both public and private multimodal responsible AI (RAI) benchmarks. The table includes metrics that range from 0 to 10, with higher values indicating better performance. This comparison is crucial for understanding the effectiveness of safety post-training and enhancing our AI capabilities across various benchmarks. Thank you for watching.